Good morning. Good morning, student. Good morning to all.
Good morning, sir.
So let us start our session. Uh, we last class have discussed computer vision. We had some introduction. What is computer vision? Uh, it is a branch of artificial intelligence that enable computers to interpret the extract information from image video similar to human perception. That is, when we see an image, we got some information, we extract some information from it, from that image or from that image. So similarly, although the computer does not have an eye like a human, it also interpret or extract that information from the image or videos. This process is known as computer vision. It involves developing algorithm to process visual data and derive meaningful insights. So there are some particular algorithms prepared for that. Uh, mm, how to process the visual data and extract information from the image or video. We have already discussed applications. Oil and natural gas, that is, the oil and natural gas companies, it is provide million of barrels of oil and billions of cubic feet of gas every day. But for this to happen fast, the geologists have to find a feasible location from where oil and gas is extracted. To find this location, they have to analyze thousands of different locations using image taken to the spot. It is not manually possible. Suppose if your geologist has to analyze each image manually, you just imagine how long would it take to find the best location. So it takes maybe months or even a year, but due to the introduction of computer vision, the period of analyzing can be brought down a few days or even a few hours. So within a less time, a geologist can analyze uh, each image rather than uh, done it manually. Hiring process also. In the HR world, computer vision is changing how candidates get hired in the interview process. By using computer vision, machine learning, and data science, they are able to quantify soft skill and conduct early candidate assembly to help large companies shortlist candidate. So also, uh, by using the quantify soft skill or some by conducting some assessment or some pre-exam, this helps the large company to shortlist the candidates. If the number of candidates are large, so by this process also used to shortlist the candidate. Video surveillance. The concept of video tagging is used to tag video with keyword based upon the object that appear in each scene. Now, image is being that security company who asking to look for a suspect in a blue van among hours and hours of footage. Suppose this is a video surveillance, that is due to this we can tag one tagging used to tag videos with keywords. It has to feed the video to the algorithm with computer vision. That object recognition searching through video has. There's a problem in presentation. Uh, so the next application is construction. For example, the electric tower or buildings which require some degree of maintenance to check the degree of rust in other structural defect. So it is not easy to manually climbing up the tower to look at the every inch and corner, uh, which which is time consuming, costly, but also is not safety. It is dangerous. Imagine that if a person on the ground took high resolution image, good camera, and take and capture the image from different angles, so that the computer vision specialist could create a custom classifier and use it to detect the flows and amount of rust and cracks present in it. Besides that, the fifth application is healthcare. The healthcare industry has adopted many next generation technology that includes AI and machine learning concept. One of them is computer vision, which helps determine to diagnose disease in human or any living creature. So, suppose there is a cancer cell in a patient body, so the computer vision also can detect that uh, cell by using the algorithms. If the input is given that a picture or a report, so it is recognize that, and it is known that there is a presence of cancer cell in a patient body. The agriculture farm have started using computer vision technology in various forms such as smart tractors, smart farming equipment, and drones to help monitor and maintain the field efficiently and easily. It also helps improve yield and the quality of crops. So there are the smart farming equipment now available, and also drone is used to help the monitor and maintain the field efficiently and easily. Military, the modern armies, computer vision is an important technology that helps them to detect enemy troops. In it also enhance the targeting capability of guided missile system. It uses image sensor to deliver battlefield intelligence and use tactical decision making. So it is also used in industry, automotive, and automated lip reading. This is one of the practical implementation of computer vision to help people with disability or who cannot speak. It reads the movement of lips and compares it to already known movement that can recorded and used to create models. So uh, it reads from the lips movement, the movement of lips, and compare it already known. So this is also automated lip reading, automotive. The computer vision technology, which is a dreams come true for human, self-driving AI analyzing data from a camera mounted on a vehicles to automate lane finding, detect obstacles, and recognize traffic signs and signals. So these are the applications of computer vision. That is nowadays it is widely used. Uh, this is due to this technology we are using uh, in different sector. Uh, Fundamental image formation, we already know there is a when we capture a picture, it is a 3D view. We can map it to a 2D, that is digital image is a 2D component, that is that. So we need to sample and quantization for the change from analog signal to analog image to a digital image. Okay, so we already know Fermicom images. So these are the advantages for a digital image. Digital image is less susceptible to human factor and gives accurate object to the object with the high details captures. Enhanced flexibility. Digital images are easy to manipulate. So once the analog image is converted to digital image, it is easy to manipulate, easy to edit, analyze as per the requirement through different software. Hence, they provide flexibility for post processing. So this is the requirement of to convert an analog image to digital one. high storage capacity. So data in digital format such as in one or more digital image can still be stored in a large amount of very with very high resolution and quality and will not suffer physical wear and tear. So if you keep an image in physically, so there may be the chances of it may be lost its quality. But once the data is converted to digital form, it takes less place to storage in memory as compared to analog system, image. Easy sharing distribution. So the digital image allow them to quickly be duplicated or transmitted across various channels and to various gadgets, helping to speed up the work. So this is the another advantages of digital image. So it is easily can be shared or transmitted. Advanced analysis capability. Digital image enable to application of analytical tools, including image recognition and machine learning, which can provide better insights and increasing productivity. So this is the analyze. You can analyze easily. You can get or extract information from a digital image easily as compared to a analog one. And the computer also extract information from a digital systems easily. Although it has many disadvantages, it suffers some disadvantages. Data size. Large structured digital image could occupy large storage space and computational power hence may be expensive. Image noise. Digital image may be compromised by noise and artifact, so it may suffer some noise, may contain some noise. No doubt there are some technique used to remove that noise. We have already discussed. There are different type of noise filters are there. Dependency on technology. So digital image entail the use of sophisticated technology and equipment that may be costly, and there may be constant need to service or replace the equipment. So it depend upon the technology. Privacy concern. The ability to take and circulate photographs digitally also poses concern because personal information can be photographed without the subject permission. So there is also a privacy issue. Data loss risk. Digital image repositories, however, are prone to data loss caused by hardware failure, corrupting softwares, or unintentional erasure. So this is the chance of data loss risk. If the hardware fails are there, or if the software is corrupted, uh, so this is the or intentional erase. So this is the risk of uh, data loss. So there are many applications of digital image, medical imaging. We have already discussed surveillance and security, remote sensing, entertainment and media, scientific research, object detection. Introduction to object detection using image processing. How can the object is detected by human vision, so the computer vision? So object detection is a crucial task in computer vision that involves identifying the location object within the image or a video. That is, if you want to search or find get information only for vehicles in an image, so you can detect that object using computer vision. This task is fundamental of various applications, including autonomous driving, video surveillance, and medical imaging. This article develops with the technique and methodologies used in object detection, focusing on image processing approaches. Let us see what are the key concepts. Object localization. What does this mean? This involves determining the location of object within an image by drawing boundary boxes around them. That you know that one example is face recognition system. Object classification. This involves identifying the category to which the detected object belongs. boundary boxes. These are rectangular boxes used to define the location of object within an image. You see here, this is image we have discussed. There are some image and it is detected by a object detector, a powerful object detector. Uh, there are different objects. Some book are there, some copies there, some person is there. So by drawing a boxes, different color, so it is recognize that. You see, object localization is another subset of computer vision, often confused with image recognition. Object localization refers to identifying the location of one or more object in an image and drawing a boundary box around the perimeter. However, object localization does not include any classification or detected object. It only uh, 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 identify the location of one or more object in an image and drawing a boundary box around their perimeter. So unlike your image recognition, this does not include any classification. So there is no classification in object localization. So you see, face detection with deep learning on a digital image. You see this is the face detection. By drawing a, you see there is a boundary, boxes are drawn. It detect that these are the faces of human. So for this, suitable algorithm is employed to detect that. So let us see image recognition and image detection. The term maybe seem similar, but technically there are the differences. Image detection is the task of taking an image as input and finding various objects within it. Okay, so this is image detection. Taking an image as input and finding various objects within it. For example, is a face detection. When algorithm aim to find face pattern in image, when we still deal with detection, so we don't care whether the detected object are significant in any way. But the goal of image detection is only to distinguish one object from another to determine how many distinct entities are present within the picture. Thus, boundary boxes are drawn around the separate object. On the other hand, image recognition is the task of identifying the object of interest within an image and recognizing which category or classify them belongs to. So, image recognition means is it a task to identify the object of interest. So, there are various objects. Suppose you are interested for a particular information. You see here, this is the another uh, example. Real-time video recognition with the different classes. They all are vehicles you see, but it is classified that vehicles, these are the car, these are the truck, using a tools YOLOV5 you see, these are the recognition tools. Let us see how does AI image recognition work. The conventional computer vision approach to image recognition is a sequence computer vision pipeline of image filtering, image segmentation, feature extraction, and rule-based classification. However, engineering such pipelines require deep expertise in image processing and computer vision. A lot of development time and testing with manual parameter tweaking. In general, traditional computer vision and pixel-based image recognition system are very limited when it comes to scalability or ability to reuse them in varying scenario and location. We use machine learning or deep learning. Image recognition with machine learning, on the other hand, use algorithm to learn hidden knowledge from a data set of good and bad examples. The supervised or unsupervised. The most popular machine learning method is deep learning, when multiple hidden layer of neural network are based on a model. So this is deep learning is a huge concept, but you know that video analysis, you see there is a image, video analysis with machine learning using another tools. So you see this image contain different component. Some person are there, some others component are there, clock is there, TV is there, and you see it is recognized by them. So this is a video, and from that video, it by using computer vision, it recognize the object is a different object. The introduction of deep learning is combination with powerful hardware GPU and enable great breakthrough in the field of image recognition. With deep learning, image classification and deep neural network face recognition algorithm achieve above human level of performance and real-time object detection. Uh, then human vision system. So this question may comes, what is how human vision? Forget about the computer vision. How human vision? So we know that the basic is that the our eye, the human eye is basically responsible, and that is the we know that our eye we can view it many object by using our eye. The human eye is nearly spherical in shape, in a 20 diameter on average. The three main part of our eye is the cornea and the sclera or outer cover, the choroid and the retina. So you see, this is the structure of a eye and different parts. Cornea, iris is there. You see, retina is there. Blind spot is there. So eye lens is there. You see. So this is the different component of our eye, a human eye, and it has different functions. The sclera is an opaque member that encloses the optic globe all around except at end anterior end, which is covered by the cornea. The cornea is top transparent cover of the anterior chamber. Choroid is the layer under the sclera, and the membrane choroid contains a network of blood vessels. These blood vessels from the major source of nutrition of the eye, and these blood vessel from this eye gets the nutrition of the from this. If a choroid is damaged or inflamed, it can restrict the blood flow of the eye, resulting the serious damage to our eye. So the role of the choroid is also to control the amount of light entering the eye, as well as the reduce the back scatter. And so we know that in this we know this is we our eye is capable of holding the some intensity of light. So if the amount of light is more, so the role of the choroid is also control this amount of light entering to the eye, and as well as it reduce the back scatter inside the eye. The ciliary muscles which relax and tighten to enable the lens to focus by changing its shape. The iris diagram that contracts and expand to control the amount of light that enter the eye. So it control the amount of light, which is the part of the chloride. The lens is a transparent biconvex structure that helps to refract light into the eye so that the image is formed on the retina. You know that when if it is the light is not refracted to that part, so image will not form on the retina. So our eye is flexible. Suppose you can see an image which is very near to you. Also, you can see at the same time you can see an image or an object which is very far to you. So the lens, the eye lens is so flexible that it can change the shape to change the focal length of the eye. So this ensures that object at various distance can be focused upon and their image can be formed in the retina. So this is the work our function of a lens. So it is slow flexible that so that the it form the image on the retina. Whether irrespective the distance of the object from the eye. If the distance is very small too, you can also view it. If the distance is very large, also you can view it. Besides that, the retina, we have already discussed the eye and the different component, different part of the eye. The retina is also is the innermost membrane of the eye. It lines the wall of the complete posterior portion of the eye. The retina can be thought of the image plane in the eye since on properly focusing the eye on an object, light from that object is passed through the lens so that the image is focused on the retina. So we already discussed that is the lens is flexible and it is so that it changes the so that the image is formed in the retina. It changes the focal length, so the uh, uh, image lies on the focal length of the lens, so that the image is formed in the retina. The retina consists of two types of cells called rods and cones. The cones are highly sensitive to color and around 6 to 7 million human eyes. So this is the you see uh, uh, the the cones are highly sensitive to the color and 6 to 7 millions of in human eyes they are present. The cones are located on the fovea or focal length, which is the central portion of the retina. However, there are 75 to 150 million rod cells which are completely distributed all over the retina. The rod cells give the overall picture of the object in the scene and reduce the amount of details. Rods are also responsible for low light vision, also known as scotopic vision, which cones are responsible for bright light vision, also known as photopic visions. So these are responsible for the low light visions, and this is also bright light visions. So one first one is called the scotopic vision, another is photopic visions. In the human eye, the distance between the retina and the lens, that is the focal length, varies between 14 and 17 mm. The reflective power of the lens increases from min to max. For the nearby object, the lens is most strongly reflective. However, the lens's eye is very flexible and it is flattened by controlling muscles to enable the eye to focus the distant object. Otherwise, you cannot view the object. So the lens's eye is very flexible, so it is flattened by controlling muscles to enable the eye. So it is, the image is formed in the retina so that we are enabled to view it. Color fundamentals. So let us in this session we will discuss what is color fundamentals and what are the different color models. RGB is there, CMY is there, CMYK is there. So let us discuss. It is also important and many times it comes in the exam. That is what is different models, color models. Let us see how the color is formed. What is the color fundamentals? Every color is defined using the three quantities that are independent of each other. However, taken together, they define a particular shade of color. The quantities are hue. Hue component of a color is identified by the dominant wavelength. The wavelength range on the electromagnetic spectrum that define the visible color spectrum between 400 nanometer that represent the violet color and 700 nm that represent the red color. So this wavelength is ranges from 400 nanometer to 700 nanometer. So 400 nanometer is a violet color and 400 nm is the depend red color. You see, these are visible spectrum 400 to 700. And you see the other wavelength, you see it is not visible. Suppose X-ray, it is less than 400. It is X-ray is 10 to power minus 1 nm. That is 1,000. So it is less than that. So we cannot view it. Gamma rays, infrared, radio waves. So it does not comes beyond this range, under this range. So that is why it is not viewed to us. So the visible spectrum only between 400 to 700, where 400 is which color? Which color? Depend. Uh, which color? Violet color. And your red is 700 red color. The other color is in between them. Suppose for take example the blue. Blue is the wavelength of blue is 436 nanometer. Green is you see 546 nanometer. Red is the maximum, that is 700 nm. And the other colors which is visible to us lies between this range. Four hundred to 700. So this is known as the visible spectrum. That is, if the wavelength, the color of the wavelength lies between this range, we can visible it. Otherwise, we cannot view it like your infrared or radio waves, ultraviolet, UV light, X-rays. Then second is saturation. The excitation purity of the color is determined by the quantity known as saturation. It is dependent on the amount of white light that is mixed with the hue of that color. So it is dependent upon the amount of white light, how much white light is mixed. A fully saturated color implies that no white light is mixed with that hue. So a fully saturated means no white light is used with that hue. Chromatosity. The sum of hue and the saturation constitute the chromaticity of the color. The chromatosity, the uh, chromaticity of the color is defined as the sum of hue and the saturation. Therefore, if there is no color, it is called achromatic light. Intensity. The amount of light actually present defines the intensity. Therefore, intensity is a physical quantity. If more light is present, the color is more intense. The intensity is more. Achromatic light. Achromatic light means which is no color. Light has only intensity but no color. Grayscale image have only intensity. You know that gray color have either the two colors, so that is have only intensity. So luminance or brightness. The perception of color is the quantity known as luminance or brightness. For example, given two colors of the same intensity, such as blue and green, it is perceived that blue is much darker than green. Okay, because the blue is available at blue's wavelength is less. Uh, Reflectness, the ability of an object to reflect light, is the reflectance property of the object. The reflectance property determines the color of the object, since we see those colors that are reflected back and not that ones that are observed. For example, an object that reflects green absorbs all other color in white light spectrum except green. So the object that reflects green absorbs all other color, only reflects green. And you will be surprised to know that there are about 6 to 7 millions of cones in the human eye, and they are responsible for recognizing colors. So 6 to 7 million of cones are present in our eye. So nearly 65% of cones recognize red, 33% sensitive to green, and about only 2% to the blue. Red, green, and blue are known as the primary color. You know that they are known as the RGB models, RGB, and nearly all other colors are seen is a combination of these primary color. So the other color, these are the primary color. The other color, sometimes known as secondary color, which is a form by combining these three primary colors in different ratio. However, there is a difference between the primary color of light and the primary color of pigments. The primary color of light are red, blue, and green, and they can be added to produce the second color of light that are yellow. So if you add red and green, yellow is produced. Magenta is produced if red and blue is added, and cyan is produced so in green and blue. So these are called the primary colors of pigments. So the primary color of pigments are said to be those that absorb a primary color of light and reflects the other two. So it absorbs only one color and reflects another two. Therefore, in this case, the primary color are cyano, magenta, and yellow, while the secondary color are red, blue, and green. So for standardization in 1973, Commission in International D Acta defined specific wavelength for the three primary color red. You know that it is a 400 nanometer. We had that image. You please recall. It is red is the last one. That is it is a maximum wavelength. It is 700 nm. Blue is around 436. It actually 435.8 nm, and green is 446 nm, or actually 440.1 nm. So the amount of red, blue, and green required to form a color are known as its testimonials by values and are denoted by X, Y, and Z. Let us see. If X, Y, Z and the testimonials of coefficient which define a color, if we define X, Y, and Z as relative values of primary colors, then these values can be founded as X equal to X by X plus Y plus Z. Similarly, Y is Y by X plus Y plus Z, and Z equal to Z by X plus Y plus Z. So it is obviously known that if we add these three, X plus Y plus Z equal to 1. So if we specify the color as a composition red and green, then the given the value of X and Y, the third one, the value of Z can be computed as Z equal to 1 minus X minus Y, or 1 minus whole into X plus Y. So add X values of X plus Y, subtract from 1, you will get the Z value, because we know that the summation of all the three is equal to 1. If you add any two and subtract from 1, we will get the values of the third one. Let us see. There is a good example. Consider the coordinate of the warm white. And the coordinate is 0.45, 0.4, and the coordinates of the deep blue is 0.15, 0.2. Find the percentage of the three colors red, green, blue, X, Y, Z. So the trichromatic coefficient X, Y, Z at the point warm white is equal to 0.05 and 0.4. So third one is calculated as 1 minus X plus Y. So 0.15. So Z is 1.5 for the warm white. Similarly, we shall find the other values. X, Y, Z is equal to X by X plus Y 0.45, Y is equal to Y by X plus Y 0.40, and Z equal to Z by X plus Y Z equal to 0.15. So here the x and y as z equal to 0.45, 0.4, 0.15. So therefore the percentage of each color would be red 45%, green 40%, and blue 15%. So this is the coordinate of warm height with the 45% of red color, 40% of green color, and only 15% of blue color. To discuss different type of color models. The principle of absorption of color of any model by human eye. This is color models. The human eye has absorption characteristics of color and recognizes them as variables R, G, or B. The color red, green, and blue are called primary colors of light. We know. Secondary color of lights are produced by adding primary colors. For example, red and blue gives magenta. This is called the red and green produce yellow, and green and blue produce cyan. So these are called the secondary colors of light. Proportion of primary and secondary color in appropriate amount produce white light. So different proportion means to form different color. Let us see. The first model is RGB model. We have different models. RGB model is there, CMYK model there, CMYK model is there. So let us first discuss the RGB model. The RGB color is based on a Cartesian coordinate system, where the color subspace is a Q with axis representing red, green, and blue. So it is like a the Q, the subspace is a Q, and it is represented in a Cartesian coordinate system. There are some x axis, y axis, and z axis. We have that picture in next slides. A color in the RGB model is therefore specified as three tuples RGB, where RGB represent the amount of red, green, and blue respectively present in that color. The geometry of RGB color model is a cube is given in the figure. In the next slide, we will discuss about that, but it is assumed that all color values are normalized, that it is a unit Q and all values of R, G, and B lie between 0 and 1. So it is clear from the figure that that is a model of Q with the three axes of red, green, and blue. The grayscale values lies on the diagonal of Q, which join the black 000 and white 111 vertices of the Q. You see, whatever discussed, this is represented in a picture. You see, black color. The coordinate is not written there, but you may write there 000. The black coordinate, you see, it is the origin, where R, B, G, basically you see G here, G axis is there, B axis there are, and R axis is there, and the origin is 000, where all the values are 0, and where the black color is formed. Similarly, you see the white color. The white color is component 111. That is, if you white color is, you see here the B is 1, G is 1, and R is 1. And you see the yellow color. The yellow color is, there is a combination of green and red. There is no blue in yellow. Similarly, you see the cyan color. The cyan color is from the combination of blue and green. That is, uh, red is not there, so you can tell it is 0, 1, 1. Similarly, see the magenta color, which is formed by using blue plus red. 1, 0, 1. So you see the blue color. R is not there, 0. R G is also not there, it is 1, 0, 0, 1. So only this is the blue color. Similarly, you see the green color, 0, 1, 0. So there is no red color, it is a primary color. So only green is present. There is no component of red and blue. So this is 0, 1, 0. So if you get a question for algebra model, don't forget to draw this Q. The Q is important, and from this Q you may write the combination of any color. Blue color, black, magenta, white, cyano, yellow, red. So we'll get all the information, all the combination of the primary color as well as the secondary color from the Q. So this is the different coordinate colors. So a color image in the RGB model consists of 3 images corresponding to each of the 3 color R, G and B. These 3 images combine to form one composite color image on a monitor. To convert an RGB image to a grayscale image, the intensity of gray pixel is given by the average of R, G and B values. The RGB color model is mainly used for color monitors and screens. Now the question arises, how do we find the composite color in RGB color model at any point? For this we follow the following steps. Pixel depth is the number of bits used in represent each pixel. If an image is RGB model has 8-bit image in each of its 3 colors, then each RGB pixel has depth 3 image plane, 8 bit per plane, that 24 bits. That gives rise to 224 color sets. Okay. So you see there is a example. In a RGB image, the R and B component are at mid. So R and B component is the mid, and G component is at 1. Then which color would be seen by a person? So this is a tricky question. You see, in RGB model, R and B component are at the mid, and the G component is at 1. So RGB is 1 mid, that coordinate system, and G is 1. Then which color would be seen by a person? You see, at a given point we have, so if R is mid, so R by 2, B by 2, and G is 1 plus G. So if you add all the things, that is half into R by 2, B by 2, G by 2 plus G by 2. So G by 2 plus G by 2 is equal to G. So taking half as common, so it is called RBG half. And RGB plus 1 is a gray, mid gray. That is, you know that R plus B plus G, all things are 1. So if all the present are, half of RBG is mid gray plus half of G. So which color will be seen? So pure green with some gray component. So The second important model is CMY. Cyano, magenta, and yellow are known that this is the primary color of pigment, but the secondary color of light. So these are the primary color of pigment and the secondary color of light. The primary color was RGB. The CMI model is a subtractive model, implementing that is subtract a color from the white light and replace the rest. It subtracts the color from the white light and reflects the rest. For example, when the white light is reflected on cyano, it subtracts red and reflect the rest. Because you know cyan is the combination of blue and green. So it white is R plus G plus B. So you subtract B and G. So the red is the rest. So it subtract red and reflect the rest. So while RGB and additive model, where something is added to the black 000 to get the desired color. CMY is a subtractive model. So that is why CMY is a subtracting model. That is, if a white light is reflected on the cyano, it subtract red and reflects on the rest. While RGB, the CMI model is a subtractive model. So you see the CMY is C is from 1 minus R, imaginary as 1 minus blue, that is R plus G plus B minus blue, and Y is from 1 minus G. 1 you know that is a R plus G plus B. So if we subtract G, that is R plus B, will get Y color. Where the RGB values have been normalized. DHSI gives the method to convert the RGB to CMI to enable printing hard copy. Since the CMI model is used by printer and plotter, you see the red color. You see the yellow. 1 minus G. You see the red color is replaced by this color. The blue color is blue, not that blue. I think that color is replaced by the yellow color, and vice versa. And the cyan color is replaced by red. You see, so they are opposite to each other. So in RGB model, in which the white color is produced by adding the three primary color, red, green, and blue. It shows the CMI model where black obtained as the sum of cyano and magenta and yellow. The inverse relation between the RGB and CMI model are also shown on these two images. The inverse, you will see that is the corresponding image are interchanged. The corresponding color are interchanged. In practice, the black is obtained by combining cyano, yellow, and magenta. However, this leads to a muddy looking black. For publishing, the black color plays an important role. Therefore, in the CMYK color model, black is added as a fourth color and where K stands for black. So basically the black is obtained by combining cyano, yellow or magenta. But this looks to a muddy looking black. It is not exactly the pure black. So that is why the black color plays an important role. Therefore, CMYK color model black is added as a fourth component, fourth color, where this stands for black. So as you know, if we combine these three, cyano, yellow and magenta, black color is formed. But actually, which is a demerit of CMI color? CMI model का demerit क्या है ना? If we add the cyano, yellow or magenta, no doubt a black color is formed, but this is not a pure black. It is this is lead to a muddy looking black. Okay, so as a black color is important, it plays an important role in color formation. Therefore, CMYK model is obtained. Black is added for the fourth color, where K stands for black. The HSI model. This color model is very close to human color perception, which uses the hue, saturation, and intensity component of color. When we see a color, we cannot describe it in terms of amount of cyano, magenta, and yellow that the color contains. Therefore, the HSI color model was introduced to enable describing a color by its hue, saturation intensity, and brightness. Hue describes the pure color, saturation describes the degree of purity of that color, while intensity describes the brightness of color. In a grayscale image, intensity identifies the gray level. The figure shows the HSI model and the way color may be, you see. This is the RGB models, and if all are the one that is of the white color, and you see that the black color is present, and in between the different color is formed, you see the red, magenta is there, cyan is there, the combination of red and green from yellow, blue and green is cyano, red and blue it is magenta. The HSI color model is represented and its relation to RGB model. The HSI triangle shows a slice from SI solids at a particular intensity. We may notice that the hue saturation of intensity values required to form a HSI color space can be computed using the RGB values. So this is all about our color models. And next slide we have already discussed DFT. We have already discussed DFT, DCT, Fourier transform, and we had also some numeric uh, questions we have discussed in the previous classes. Let us start another topic: transformation, 2D transformation. Let us uh, let it give me some 2 minutes so that I will open another file, another PPT. Okay. 2D geometric transformations. Basic of 2D transformation. Rigid body, it is also known as rigid body transformations. Uh, So there are different type of translation that there. Translation, rotation, scaling. Um, the transformation means you know that is the translation is used to change the location of a there is suppose object you want to change its location, the translation is used. Rotation. If you want to rotate, if you want to rotate an image towards right, towards left, towards clockwise or anti-clockwise with specific angles, 60-degree, 45-degree, 90-degree, 180-degree. So you can rotate that object. And scaling. Scaling is used to resize. If you want to change the size of the object, the scaling is used. And homogeneous will also the objective of this session is the homogeneous representation of coordinate. What do you mean by homogeneous representation? As you know, the image is a 2D x and y components, but we use a homogeneous, the third row and third column, to represent an image. So this is known homogeneous representation, and it is used to basically to perform the 2D transformations easily. 2D composite transformation. That is, we can apply multiple transformation in a single object. That is, you can translate followed by rotation to one object. So this is known as composite transformations. Composite transformations. And the other transformation are reflection and shearing. The reflection is the mirror image. That is, if we put a mirror in front of an image, the another image is formed. That is the mirror image of a reflection. And shearing. The shearing is used to change the shape of an image. In previous, it is scaling. Scaling is used to size, and shearing is used to change the shape of the image. Suppose the shape of image is a rectangle, you can change it to a square. And if there is a square, you can change it to the if it is a rectangle, you can change it to the parallelogram. So this is your shearing. So there are 5 different 2D geometric transformation is used: translation, rotation, scaling, reflection, and shearing. So in this, our objective of this session is we'll discuss about these 5 type of transformation. Besides that, how to represent in homogeneous coordinate system, and also 2D composite transformation. That is, how can we apply more than 2 transformation, one followed by other simultaneously in a single object, on a single object. Geometric transformation, sometimes also called modeling transformation. It is also called modeling transformation. Geometric transformation, changing an object position, is known as the translation. We know that translation is one type of transformation, geometric transformation. But here, if you want to change the object's position, suppose it is x and y, you want to change in p to p comma q. From x to y to change to p to q, we use translation. That is, if you want to change the location of your image, use translation. Similarly, orientation. If you change to orient or rotate your object towards a direction, either in clockwise or anti-clockwise, with respect to origin or any other body, uh, through specific degrees, specific angles. It is 45-degree, 180-degree, 90-degree, 60-degree. So this is called the rotation. So to perform this, we have to use the rotation transformation. The last one is size, scaling. The scaling is used to change the size of the object. The size of the object. That is, if the object size is small, you can enhance their size or you can reduce the size by using a geometric transformation scaling. Other transformations, reflection and shearing. As you know, reflection, that is a mirror image. That is reflection. If you keep your image in front of a mirror, so uh, this is known as the reflection image. And shearing operation, the last operation, shearing, which is you want to change the shape. Shearing operation is to change the shape, not the size. The size and shape are different. Shape means that if there is a rectangle size, you want to square size. There is a rectangle size, you want to parallelogram size. So the change of shape is there. So this is known as your shearing operation. Let us see one by one. Basic 2D geometric transformation. You see the image there. There an object point P. Point P is in original position. P is the original position of that point. We use transformation translation T so that the object is a change in location P to P dash. So now the new position of that object is P dash. So if you want to change the location of an object, the translation geometric transformation is used. So you see the P, the coordinate of P is there, and we applying T, it is converted to P dash. So the suppose the coordinate of P is xy, and after translations it converted to P dash. X dash y dash, a new coordinate. So x dash is now calculated as x plus tx, and y dash is converted to y plus ty. So you need know that if P is the initial coordinate xy and it is changed to P dash x dash y dash, so it is calculated by x dash equal to x plus tx, and y dash is obtained by y plus ty. So x dash and y dash is the new coordinate of P dash. So if we represent in a two-dimensional matrix, so P is equal to xy, that is x and y is the original component of P of the object P is x and y. So now it is converted to P dash and P dash, that is whose coordinate is x dash and y dash, and T is the Tx and Ty, the translation factor Tx, that is Tx. Why it is Tx? Because the translation factor along x axis. So that is why we add Tx to x. Similarly, Ty, the translation factor along which axis? Y axis. Ty. So P here equal to P dash equal to P plus T. If you add P plus T, you will get P dash. You see, P dash equal to P plus T. That is, if we add P matrix and T matrix, so we will get P dash matrix. The X plus Tx and Y is equal to Y plus Ty. So if we add the values of Tx and Ty with the original form, that is known as your 2D geometric transformation or translation. So in the translation, we are able to change the value from one point to another point. So initially it was a P, now it was in P dash. So translation moves the object without deformation, rigid body transformation. So without changing anything, only it changes the object from one point to another, from one location to another. So if we want to change the location of one object from one point to another, from one location to another, 2D geometric transformation, translation is used. So in previous example, only a point is changed. A point is translated from one position to position. Suppose the point was in P, we are able to change to P dash in new position. But what in case of a line? So as you know, a line is nothing but it is a combination of points. So to move a line segment, suppose instead of point in there is a line. So we have to apply the transformation equation to each of the two line endpoints. We need not to apply translation to each of the points in the line. We have to only apply the translation to the line only. Okay, to line endpoints only. Suppose the line point is P and Q, we have to only apply the translation to P and to Q. So to move a line segment from one location to another location, we should apply the transformation equation to each of the two line endpoints and redraw the line between the two new endpoints. So if we apply the transformation or translation equation to each of the two endpoints, we will get two new endpoints. So join that two new endpoints and we will get the line in another location. So in this way, we can move a line segment from one location to another. Similarly, to move a polygon, suppose there is a triangle, there is a rectangle, there is a hexagon or pentagon. So to move a triangle, suppose there is a, take example of a triangle. It has a three distinct point. A triangle, you know that triangle has 3 points. So we have to apply the transformation equation, translation equation to the all the vertices. As a triangle has 3 vertices, we apply the translation equation to these 3 vertices. And we get another 3 new vertices. Join these 3 new vertices and we will form a new triangle. And the new triangle is not is the is in a new location. So in this way, we are able to move a triangle. Similarly, a rectangle. We have to apply the transformation equation to all the 4 vertices of the rectangle. So after that, we will get new 4 vertices of and rejoin that, redraw that, you will get another rectangle in other location. So it is rigid body transformation, no other information, that is no other is change. The area will not change, the side of the length of the side will not change, only the location is changed. Suppose the rectangle is one place, it is only translated to or replaced to or moved to another location only. No length in sides, no area will not change. The other will not change. So To move a polygon, apply the transformation equation to coordinates of each vertex, and regenerate the polygon using the new set of vertex coordinate. Either it is a hexagon, either a pentagon or a decagon, use the same formula. Apply the transformation only to vertices only. You will get a set of new vertices, regenerate, redraw it, and get the new set of vertex coordinate and get the new image. Similarly, the second transformation is rotation. So rotation is used to orient an object, to rotate an object, either in direction, either clockwise direction or anti-clockwise direction through certain angle theta. You see here, this image gives that there's a image, and with that point, we can rotate that to either towards clockwise or anti-clockwise through a particular angle theta is. And this is two-dimensional rotation. We are able to rotate an object to particular angle. So applying the rotation, we can use, we rotate an object to a particular angle. But the 2D rotation, we need rotation axis. In which axis we want to rotate? With respect to which axis? Rotation angle theta. We need that. So the angle is required. How much the object to be rotated? 60 degree, 30 degree, 180 degree, 90 degree. So this is the, we need rotation angle. A rotation point or pivot point, with respect to which point we have to rotate. Suppose this rotation is a origin, we can tell the rotation of the object with respect to the origin, 0, 0. Otherwise, you can also rotate that object with respect to any other point other than the origin. So that is called your pivot point. So to perform the rotation, we have to need these components: the rotation axis, rotation angle, and rotation point or pivot point. So we'll discuss. So please write your name and number in the board, those who have not written only. Please wait a while. I will take the snapshot.